It's fine. Are you getting before you?
Oh, here, there is a remote. You guys should know what is getting recorded, right? Oh, I can do this here. Yeah. That's... I think it's been sometimes since I taught in this. Does it? Okay, yeah. So yes. It's not working out.
That's funny.
Did you go in the, do I need to turn it?
I have to sort of zoom out.
I don't know.
Or but it's like facing me.
It's like, oh,
Seven. If now we're facing it.
we're tired.
I thought it zooms out. Okay, I don't know. I guess not. Okay. Okay.
Now we all get our. This is fun.
Now let's set the blackboard.
Why are you recording it just for fun?
No, because one of the problem doesn't have.
Huh?
One of the problem doesn't have a solution.
Homework.
Oh, okay.
I was thinking of recording it yesterday, but then I thought this is much better as interaction. Otherwise, it's very boring to write the solution.
Oh, what it was zooming out.
Is zooming, all right? Yeah,
Mhm.
I think that's good enough. It's set this and
Oh, shoot, the homework date was due tomorrow.
No, it's due Thursday.
It still says it's due tomorrow. Oh, you moved it?
it says tomorrow.
Mhm.
What did I say about that? What?
You said it's due the same day as the. this meeting.
Oh, that's a mistake. Remember to change it. I think it's mistake. Can you guys do me a favor by any chance if I forget to change it?
Oh, I'll let you.
Uh-huh.
I said I'll let you know.
Yeah, just drop an email if it doesn't get done by 9 o'clock today in the evening. I intend to do it. Oops, I'll get otherwise 50 emails. Okay, so who is this? Let's change it back. Okay. So what did it?
But I do have a question. Did you say like, kind of, not curve, but you said you make adjustments to our final grades in the class?
No, not at a personal level, no.
What's gonna happen?
Uh,
So basically, whatever your, after the last midterm, whatever your grade is, and then you take the final, whatever you get on the final, like your grade, like on the last exam, that will be your grade. Like he'll change like curve, like make the class curve. So like, you won't like go way down.
Usually
It'll go
not.
way up.
Yeah, I try
But
to keep.
it's pretty even with like. the quizzes, the homework, the midterms, like.
You say, oh, like,
Percentages in there right now, like that's what it'll be.
Yes. So the general, okay, here's after midterm 3, let us say, like all this becomes important when your grade is about 88, let us, or let's say before that, make it 85 is your grade, raw grade, I mean, not the one that you see on your computer. It's usually less than that, it's about 85 or something. Then I come in and say that, okay, I will give about 20% of the grade that you lost. So out of 15 points, I give about 2 points back, 2 plus 1. So 15, 2% be about 3 points. So that makes it 88. So that's your grade, but I have given you that 20% remember, and that depends on your quiz grade. So it's 88 now. Now, if it is 88, there is a reasonable chance that you can become an A. Now, what happens? So what do? I again give a final. I take back that 20% that I've given you. I take it back. You take the final. Again, a new grade comes in. And from that point on, now I curve. Right? And that curve becomes very tricky because for some reason, the final exam really changes the grades for many people. Like it's not at all, the whole semester is different and the final exam really disturbs the grades for most of the students. I try to minimize that effect, but I have only one parameter, that is I can give back some points. And I have to choose a cutoff. Now, how I choose is that let's say there are few students around 89.2 or something. So I look for a small gap. If I do 89.2 as a cutoff, 89.1 seems to be not fair. Right? So I look for a gap which is reasonable. Like if there is a gap of 89.4 and 88.6, that's a gap, right? So then I'll put the cutoff there.
You said you dropped one homework
Yes, one homework.
and anything else.
That's all. Yeah, that and those things change. Like maybe 2 homeworks can be dropped, but usually it's 1 homework. There should be a reasonable reason to do the otherwise. It's usually one homework and many quizzes. I drop a bunch of quizzes. Like because there are so many of the quizzes, I don't mind dropping more quizzes, but homework usually there are only about 10 or 12. So it seems reasonable to drop 1 at the most to do that. So that's what happens. And there is sometimes very few number of times, even with this parameter, if I have not been able to help students because of the final exam disturbances, then I'll come and grade final exam separately. So boost the final exam and boost from the overall boosting also. So that, but whatever I do, that's done for everyone.
Yeah.
So that's the, does that make it clear? And I also say that after midterm 3, if your grade is below 87, most probably the chances of getting a is less.
Very small.
Is very small. Probably, I mean, I don't know exactly what is the thing. You probably cannot make it even if you get 100 out of 100.
On the final.
On the final, you cannot. I think so. Something like that. There is a cutoff there.
Okay, we need to you have to go above the 87, probably have a chance of getting the name of the class.
Look it up. I mean, just check if you have an 87 and then put in your grade in. So I usually say that if it is 87 plus, keep trying. If it is below 87, then be judicial, then concentrate on another subject. Like, because you'll be putting in a lot of effort if you want to make 87 to an AA. So be judicial about that. Make the right call. Right. So, okay. Problem 1, right? Can you do this question simple? Okay, so this is problem one. Can I? No, I cannot get that problem here, right? So we have this, there is a magnetic field that's going into the board. It doesn't tell you. So the magnetic field, let's say it's going into the board. And there is a circular loop of wire, and it has a radius R, I suppose. And goes from, so B is equal to 0.5 Tesla, and the radius. So the rate at which it changes, the initial R initial is equal to 15 centimeters. And the rate at which the radius changes, R by dt, that's equal to 72 centimeters per second. Okay. So, yeah. What is the direction of the so recall the voltage that is induced, which is also called EMF. This is also called EMF. Induced voltage is equal to number of loops times there's a negative sign in there, but if we're talking about the magnitude, we don't have to worry about that. And the rate at which the flux changes, the flux is B dotted with A. These two are aligned. If this is perpendicular to the plane, then area is in the direction of the magnetic field. So you have number of turns d by dt of B times A times cosine of 0 degrees. A is pi r square, that's area. B is a constant, so it's, and there is a negative sign. And the dA by dt is equal to pi 2 pi r dr by dt. Pi r squared, derivative brings in a factor of 2, and then dr by dt. So it's 2 pi r. dt. So the induced voltage at that instant, that in the beginning, it depends on this radius notice. So the initial induced voltage would be the initial. So let's say magnitude would be equal to the number of loops. I think it is just one, right? One loop of wire provinces. An elastic conducting material is crushed into.
Wait, why is it first line zero?
Because this is an area, its area vector is either coming out of the board or going into the board. If it is going into the board, magnetic field is also going into the board, then it is 0. So plane.
Wait, say that one more time.
So the plane, the vector associated with the area is perpendicular to the area itself. So area is in the plane of the board. It is going into the board if you want. There are two choices. Choose it along the magnetic field. It will only change the sign here, but we are interested in the magnitude. So, so that's
So
makes
it'll
it
always be in or out of the board.
no, it will not. Okay.
What's an example where it wouldn't be?
So for example, in this case, so let's say this is the magnetic field. And that's your loop. This is your area vector. That's the loop. Here, the loop is perpendicular to the magnetic field. So that's what it is. That's my angle. 0. Okay. So n is 1. Number of loops, there is only 1, and b we said is 0.50. Tesla 2 pi. Initial, so this I means this voltage changes with time. As R changes, its induced voltage changes. Our initial is 15 centimeters, so 0.15. And dr by dt is 72, but that's 0.72, because this is 0.15 meters, and that's 0.72 meters per second. Oops.
When did we go from dt to dr dt?
Because this b is a constant that stays intact. dA by dt, rate at which the area changes. So area is pi r square. So rate at which it will change is the derivative of this. So it is 2 pi r times dr by dt. So I just substitute that in here. Oops. Okay, and that's equal to. Fine. 0.34 volts. Such a reduced voltage, and we also need
Wait.
you don't really need a direction, yes.
You have dr dt is equal to dt. Why did you put 0.72?
That is.
So,
Oh.
Sorry.
Yeah.
now we need to know the direction of the current. The direction of the current is in such a way that it will oppose whatever the system is trying to do. So what is the system trying to do? It is trying to shrink, correct? So it is shrinking, so its flux is decreasing. Think in terms of the magnetic field. Magnetic field is decreasing, so the system will try to increase it. It will oppose it. So it will try to create a magnetic field inside the loop. It is opposing, so it will try to increase it. So it's trying to increase it. Right now, I said it wrong. It's going to increase it, so it has to be in the same direction. It's going to increase it, so put the magnetic field in the same direction.
Wait.
The
So it's
magnetic,
going to shrink, so we want to go against the shrinking.
not shrink. You want to go against the shrinking, but what the system can do is only increase the flux. And the flux is the magnetic field. Decreasing the flux, it will try to increase the flux. Okay, it cannot change the area, if that makes sense.
Yeah.
Okay, so since flux is decreasing, it will try to increase the flux, but not by increasing the area, but by increasing the magnetic field. That means it will go in the direction of the magnetic field. So this is going to be the induced magnetic field, if that makes sense.
How do we know that it wants, wait, how do we know that the flux is decreasing?
Because it is shrinking, area is decreasing, flux is magnetic field times the area. That makes sense. So magnetic field tries to increase, and if that is increasing, now you hold your hand and try to get which way should the current go so that your fingers are going in, and using your right hand, you say that, oh, this must be in this direction. So that's your current that is induced.
So it wants to do the opposite, or it wants to upload, like do the opposite of what the flux is.
Yeah,
doing.
so maybe let me write it down. So area is decreasing. Like that's what the system is doing. Right? Area is decreasing. That means that flux means phi, right? It flux, right? Flux phi is decreasing. Flux can decrease by magnetic field, area, or angles. If flux is decreasing, magnetic field, induced magnetic field, it's going to try to increase is along the external. So this is the external. Just giving it a name, and that's the induced. They are in the same direction. So B is along the direction of the external field, and then you decide the current. If B has to be in that direction, use your right hand rule to get which way should the current be. There are only two possibilities, clockwise or counterclockwise. And then you say that I has to be clockwise. Now notice that this problem depends on the choice of the B external. I chose this B external. The problem, it did not tell me that it is going into the board. So it will depend on the diagram everyone draws. Some people, some half of the students would do it coming out of the board, but for their diagram, it should go in the direction of that. So it is relative to what they draw or what they say it is. Either way, it has to be, it should not be ambiguous.
So if the radius was increasing, everything basically would be the opposite.
Yes, mostly, yes, I think so, yeah. If
Because
area was increasing, then flux is increasing, then B is in the against the external field, and then it will be counter. That's good. Good one. Yeah. Is that readable?
Yeah. So then B would be internal, B would,
Then B would be,
meaning coming out of it.
yes, it's good. No, it's readable.
And current would be counterclockwise.
Mm-hmm.
And the EMF is induced by the loop. Wait, didn't we not need to find that answer? Because didn't it just ask what direction is the current, so couldn't we have done all of that without?
Oh, the second part is asking.
Oh, that's the EMF.
So maybe this is A. That's B. This is for homework. Eat.
Too far.
So. Okay, good.
I just trying to say that, but it is.
This is almost 8 problem. 2. There is a diagram associated with this one.
PDF.
This- yeah. There is a resistor. And there is a rod that you pull in. And you're pulling it out of it, so you can see these. And L is given to you, V is probably given, R is probably one.
L is given, B is given, B is given, R is given.
It is B extra. Yeah, so. This is all given to us. Right? And we're asking for the induced power. What is part A? Question?
Is the magnetic flux in the loop increasing or decreasing?
Yeah. So flux is area times, so area is increasing. Area is increasing. That means flux by V is increasing. If flux is increasing, now the induced magnetic field, so it's increasing, that has decreased, right? So induced magnetic field is opposite to the external. So that means induced magnetic field is this. Something.
How do we know the area is increasing?
Area because you're pulling this, so this is
Okay.
the loop that is formed.
Okay.
Pulling it to the right, so area is increasing. So flux is increasing, induced magnetic field is opposite to the external magnetic field,
We know air is increasing.
because this is increasing, right? The loop's area is increasing.
So if the area is increasing, that means the flux is increasing.
Flux is area times the magnetic field,
Mhm.
like how much magnetic field is coming or going in. Will increase if the flux or like in. So this means that now induced magnetic field has come out, so hold the wire in such a way that fingers match with the induced, so current has to be in this direction, that's the I. So I is counterclockwise. Make sure this is not, there is no ambiguity in it. Don't say left to right, because this left to right means that there it is right to left. So make sure you make it very.
And how do we know that it's counterclockwise?
Use your right hand rule,
Oh.
like hold the wire in such a way that the fingers point, so this is coming out of the,
Okay,
so thumb is pointing in that.
okay.
Wait, what's the flux again? You said area times.
Area times magnetic field times cosine of the angle between. That's the,
What is the direction of the induced current?
yeah, so that's this, so it's part B is the, so this is part A, area is. That's
I'm
part,
trying to process.
Huh?
Yeah, he's labeling.
Okay, I was like. I'm trying to process.
yeah, so that's A, that's B, And C requires some work.
So B is asking to determine what is the direction of the induced current. And you said you know about because it's the. You only need to know the direction of the magnetic field, basically to find the direction of current, right?
If you know magnetic field,
You mean this one, this magnetic field? Or that magnetic?
The given magnetic field.
No, right? Like. We need to know the flux, whether it is increasing or decreasing.
are you saying how do we define a current? Are we following the V?
Yeah,
That's
we're
how we-
following the V.
So you're saying how the arrow's going that way? We're to go that way, and holding it right here, you're supposed to be going that way. So that's why if you grab the wire, you can't grab like this.
Yeah, but we're finding the current, so we don't know the current's going that way yet.
No, maybe let me, okay, the question was, is this the guiding principle? Yeah, you start from here, but the main question you ask is the flux in the loop increasing or decreasing? You're trying to pull the wire to the right.
So flux is increasing, so you said when flux is increasing, it's opposite of the magnetic field, but when
Yes.
flux is decreasing, it's the same as the magnetic field. I need to write that down like big stars. Flux increasing, same direction as magnetic field.
I think it's opposite. You're writing it wrong.
No, when flux is increasing, it goes opposite of magnetic field.
Oh, whoops. Opposite as magnetic field. And when decreasing, same direction as magnetic field. So because it's increasing the fluxes, I'm gonna go out of the board. And because it's going out, that's how we find the current. Okay.
Just sad that.
Okay. Determine the magnitude of the induced current.
Oh, that's not right, right? I thought we already have which one and four, so that's not changed.
It's probably a hassle to change all the clocks in the buildings.
I bet they don't.
Oh, they do.
They do? They
They
do
do.
every clock.
Yeah, they come and change their stuff, it's supposed to. They'll do it for a weekend, it's unusual.
Right. All right, I'm ready for C. Sorry, just my brain.
You sure?
So C is you want the induced magnetic, sorry, induced voltage. Induced voltage is, let's talk about the. And rate which the flux changes. And this is the induced voltage or EMF, and that's also equal to I times the current R. Right? If we are interested only in the magnitude, this will be equal to magnitude of I would be equal to 1 over R. There is no sign there. N d by dt times the flux. That's equal. So there is only one loop here, so N is 1 over R d by dt times flux is magnetic field times area is, let's say this is X times L. And cosine of 0 again, because the direction perpendicular to the surface of the loop It's making zero
it's-
degrees with respect to the
It's,
magnetic field.
oh,
Like if you have this plane, area is perpendicular to the area.
okay.
Right, so you can either make it up or down, that will change the sign, but we're talking about the magnitude. So
Why would it be 180 though? Because it's opposite.
that's what I said.
Oh, it is.
Two possibilities. So 180 will be minus sign. But I'm taking the magnitude. It doesn't matter.
So it is 180. It's just the magnitude.
There is an ambiguity in there when you say that this is an area,
Mhm.
and I say that the area vector is perpendicular to that. This is also perpendicular. That's also perpendicular.
So should we just use the?
Either one of them. Pick your favorite, it doesn't matter.
Okay,
If it comes out negative, remember this is magnitude, so it will not change. There is a rule for that, but that depends on the right hand rule again, but I'm not going there. It will only confuse you more. This is equal to n over r. D is constant, L is constant, and dx by dt is v. Dx by dt is velocity. So it is d, v, L, and cosine 0 is 1. So we can plug in numbers now. So it is number of turns is 1. Resistance is numbers.
Resistance is
0.4 ohms. Magnetic field is 1.2.
yeah, which is
1.2 Tesla. 5. So I think it should be meters per second. So yeah, 5.0 meters per second. And the length is 10 centimeters. I think.
wait, how do you know n is 1?
Because this only has one loop, right? So if there was by any chance 2 loops here, if this was making 2 loops somehow, but it's hard to make it in this scenario. Then,
Usually it'll be 1.
not necessarily. There are, for example, when you have a generator, then you have more number of loops. There are at least 1 in 4 problems will have n not equal to 1. So look for
But would that be like, would you say n equals 2 or? would you
not
have
n, it will typically say number of turns.
Number of turns?
Number of turns, that's what in a coil.
Because it's not that there's more wires, it just goes around it more times.
No, there are more wires. For wire,
Oh,
like it's usually a coil. If you've seen any electrical circuits, there will be more coils. It's physical coils. It's
And-
not the current going many times.
and you said it'll say what usually?
Typically, it will say that the coil has so many turns or the wire goes so many times. Something in the order. So that's 3 into 5, 15, so 1.5, I guess. Yeah. Okay. Having 2 problems. Nothing else.
Well, we talked for like 20 of them before we
Yeah.
started.
Yeah.
Why is this in? Oh, it's S for current. I feel like the closer we get to the test, the longer these help sessions take, because we're like, okay, we really need.
I think you do 1. Do 1 and call. 1 and call is this word, 2 and call is that word. Work.
you had it backwards. Columns that one is this one.
No, 1 call,
Oh.
2 call, 2 call, 1.
Oh, I see, you did not specify that.
Definitely said one call.
I thought, I got some.
All right, it's late.
Like you said, we're all.
No, it is tricky.
I'll have to tell her. For that situation. But for now.
I might have said it in the wrong order.
You remember when April gave you asked for a chord and she gave you like a cylindrical?
That's okay.
I'll take it to class. We'll bring a chord.
I can't talk about
That April.
I think just for that class. You can say the stories about everybody in class.
That's right. This gets a lot of clicks, by the way.
Oh,
The
God.
homework gets lots of clicks. Like my lectures, I think it is 1, 2, and this gets exact 45, 46, like 45 students, and it's about 40, 50.
Yeah, don't check her weight.
So yeah, no, there's nothing wrong. And even the lecture that I always used to pay attention on in the beginning, and it would be only 1, 0, 1 and all. So I told my nephew that, see, there's this lecture, no one looks into it. And he's young, like he goes to school. He said, have you ever noticed just before the exam? And I never used to pay attention to that. And I did do that. And right before the exam, all of them would start getting clicks. That really happens, but it's not as much as homework.
Yeah.
Okay. Problem 3. Phy's functions also. Determine the direction of the induced current. Okay. That's the problem. One more maybe. Okay, so first it starts from here. Let's do this. And that's moving that way. And yeah, let's say that's A, right? First of all, is the flux increasing or decreasing as it is moving at this point here? No, because there is no magnetic field, right, in this region, Once you-
talking about inside.
Yeah, not that until then, right here, before it enters.
Yeah.
There is no magnetic field, so no flux, and it's not changing. So B is equal to 0. So B external is equal to 0 and not changing. And not changing. So that implies flux is equal to 0 and not changing. Like just being 0 is not sufficient. It has to be changing. And if it is not changing, that means induced current that implies induced current is equal to 0. That implies that the induced voltage is 0. Exactly.
Yes.
Next, let's go to part B. So
Wait, but don't we have to do it for each of the instances?
yeah, we have to. So this is the first instance.
Oh, you're just going through the first one, all of them for the second. Okay.
So I don't think they have labeled it, or I have labeled it. So what? So, and this next is this. And now if you notice, the flux is decided just by this region, right? There's flux only in that region. So area is increasing, so area increasing. That means flux is increasing. And if flux is increasing, you guys want to try?
Then it's going.
No, first you have to decide B induced, right?
Yeah.
Is it, if it is increasing, B external is going in, so it has to oppose it, right? So B induced is opposite to the external, and then comes your point that induced voltage now is opposite, that means it is coming out, right? That's might be induced. And then you use your right hand rule, and that's coming out. So I need my fingers to come out inside of the loop. So my thumb is pointing this way. So that's my I. So I is then I is counterclockwise. Is that true?
Yeah.
That's induced current, and we have to get how much voltage is induced. So V induced is equal to, now here is a situation where it is very easy to put number of turns to be about more than one. I could have said there are 5 turns in this loop, and that's easily n changes. So induced voltage is n times B times V times L, same as earlier problem. And that's equal, number of turns is 1, magnetic field is 1.2, everything else remains the same. 1.2, 5 meters per second, and L is 0.10. So it's 0.6 volt.
How'd you start doing math?
Huh?
How'd you get so good?
It's been,
Mental math.
He's just joking, he already like, they put in these numbers, so he knew, so you could just say it and like, look like he did it.
in my
No.
wife is 10 times better. She says I'm very slow.
Really?
Yeah.
I'll be like,
But she tells me a number, telephone number, to purposely tell it very fast, and I don't get it. I cannot get it. So I'm slow. Yeah.
Is she a professor as well?
She teaches in journalism.
Okay.
Do you know there's a
Yeah.
community college here? She's physics.
she does physics as well?
Yeah, yeah.
Wow.
One of the students in our class,
Jake? Your tell?
correct, Jake,
Yeah.
yeah, she has taken class with her. That's what he mentioned once.
Did she say, or did he say that she was harder or easier of a teacher?
I would guess that she's harder, yeah.
Really?
Yeah.
Really?
That's what I would guess that's what. Her standards are high. Today in the morning,
He's like, I don't reach them.
like today morning, I got in physics you publish, right? You write an article and then you submit somewhere, and so before I submit it, she tells that this is not that great a work. And she was an advice. It was not that she was like she was telling. I mean, I had a friend, she was saying that, oh, be careful. And I said, no, this will go through. You see, and it got rejected today morning.
Oh,
He was right. So I'm saying, yeah, typically she has a good, good feel for this thing, girl. I should be more careful in listening to her. I should pay enough attention.
She's like, I told you so.
Yeah.
She said you get your own dinner now.
Okay, hey. So, number C here. So now we're at the center, so somewhere here. And here there is a lot of flux now. When you're moving to the right, tell me, is the flux increasing or decreasing? Hmm?
It's staying the same.
Staying the same.
Oh, because in the middle it has.
It's constant.
right? It's not changing, right? Same, like magnetic field is the same, area is
Okay,
the
'cause
same.
There's no other like.
Yeah.
That line moves, it can get bigger, but
Exactly.
there's no like other line. Okay.
Correct, right? So flux is not changing, no work needed. So no current, no voltage.
Okay.
So flux is not changing. Flux not changing.
Okay, that makes a lot of sense.
Right?
That's just because technically the line it's.
Isn't extended.
It's moving the area like
Correct.
of the loop
Loop.
that we're already having, like, yeah, okay.
Exactly.
Okay.
Like, notice that 200 years back, even though that's a simple idea, that was a revolution in a sense. Like suddenly you can create voltage, pretty much like what you do in internet. You make a small change in something and then that's it. New technology that comes in. So it was like that 200 years back. So anyway,
We call it witch and burn up station. Bring down the calculator, it's over with.
okay, flux not changing, so that implies
Her name's Ashley.
I don't think I can most of the sentences.
No, I think you should.
Right? Yeah, it's creating time. People are gonna show up.
I guess this will have really go viral because
Yeah.
for a change, this is not the boring physics that's happening.
Maybe I should tell my able to. Tell my baby.
Okay, B. Okay.
Just name dropped.
Okay, is the flux increasing, decreasing? In this,
Decreasing.
right, good. So flux is decreasing. So if flux is decreasing, what happens to the induced magnetic field?
It goes in the same way.
Perfect.
Yeah.
Induced D is along the external. Right, so along, so that is along, right?
I don't think I've answered all my questions correct for myself in so long, and I just did. So.
So B is along. Now tell me what should be the direction of the current. So B is in. What should be the direction of the current?
Clockwise.
Right, perfect. Right. It's I is up. You get the pattern, right? It's the same thing again and again.
Yeah.
Right. Find out if flux is increasing, decreasing. B is either along or opposite, and I is clockwise or counter. Oh. So that's your current, but then you have to do the induced voltage also. Right? So induced voltage is equal to N times B. It's the magnitude that is important. PVL, right? Everything remains the same, except that the current is going in the opposite direction. Here it was going counterclockwise, it's going clockwise, but the induced voltage will be the same. And we have already plugged this in. 0.60 volts. E. Here. Okay. What's the flux?
Not changing.
Not changing, it's 0. Flux is 0 and not changing, or it's not changing. So I 0. Okay.
I'm pressing two, copy,
two copper.
two,
The bottom two, there are two twos, not this one. Yeah, first two, this is camera. Okay.
no, two. So one, no, two, copy.
I think it is not pointing here.
Sad,
Okay.
one day.
Okay. This thing take forever.
There's only 6 problems.
Oh, so then it's fine.
Oh, you can take off problem 6 and we can just do 2 more.
No, we'll
Why?
finish it.
Why would you say that?
I'm taking off the homework. Get off the test.
Oh, we did 6 things.
We did.
Yeah.
Six, we can skip.
Oh, so-
She goes,
Oh, five also we did in the class.
No, we didn't.
Are you sure? We did?
Five, the transformer, we did in the class, I don't remember unless, there's no other class to teach this thing.
So we don't need, maybe I'll just.
we do need 4.
Yeah, the board is important, right? That is the whole camera purpose for.
Yeah. Oh, I thought you wanted.
You could just crop this video to only 4 if you really need it. We'll be good this. We'll be good.
Or you can put it like a description. Go to like 1 hour and like.
Mhm.
Yeah, that I plan to do. So,
But and then you should also say, but if you want to be
Listen to the comment.
listening to the commentary and have to put loud,
I don't think so that people will find us as funny as we.
that's kind of true.
You know, if you're really tired, you make edit something.
That's true.
that's right. It'll be better than me making the video in the night and see almost half asleep.
They're gonna skip the video. I wish they just stop freaking talking.
That would be, if I watched it, I would be, oh my god.
Like, I just don't feel it. People like judging like a movie, you know, like giving it commentary, you know, those type of things.
Not a cool kid in this movie.
Definitely.
One of the views going in, out. Okay. Now here, the main point is that there are 2 loops. So we have to first make a judgment on what is, this is going to be replaced with. You remember we did a very similar circuit like this without the magnetic field. Like we had something like this. And that's R1, R2, R3. And this is V2. That's small value. That's V1. But notice that this could have been in either direction. I could have had this too, right? That was. This could have been in this direction too. So we have to decide that based on your V1 and V2. So let's look at V1 first. Is the flux decreasing or increasing? So flux is decreasing. So that means the induced voltage or induced magnetic field, it is decreasing, so it has to go in, right?
Yeah.
So that's V induced. Okay. That means your current will be like this. So that's going in this direction. Which means that the voltage, this is higher potential. the higher potential to lower potential, right? So that means the magnetic field or the voltage here is going to be higher potential, lower potential. Current goes away from the higher potential. So I chose this to be in this direction since the current is going up. Is that clear? I deduce the current and then accordingly put my voltage here. Is that clear? And from that point on, we just can do the old story, but first let's decide on this too.
Is decreasing, so flux is in the same.
Yeah, and maybe I can write this down, like,
Wait, how did you say current is going up? Because I thought we were doing it like.
yeah, let me do that. Loop one, flux is decreasing. So induced magnetic field along the external, right? The external is going in, the induced is going in. So next I use my right hand and say that it is clockwise. So I is clockwise.
Wait, how did you do it this way?
Uh,
Okay,
Oh, because it's saying, so the current, the B going this way, when you current with your fingers, it's going into the board.
thought we were doing it like this.
No, look at the arrow. The
Arrow has to go in.
So our fingers have to curve this way.
You should have, my fingers have to go into the book.
Yeah, so we'll do that way.
Not voltage, current. This
Right,
is the
whatever,
current.
yeah, sorry,
Current goes this way, right? Here it goes this way.
yeah.
So it will go here this way.
Oh,
So that's your voltage. Clear?
yeah.
Do the same thing here now. Flux is
Increasing.
increasing. So flux is increasing means induced magnetic field has to go opposite. That's here the induced. So the current is going this way. Right? Say this way or this way. Right, so that means again this is this way. That's it. So loop two. Loop two means on the right side. Flux is increasing, so induced magnetic field is opposite to the external. And that means I is what is complex. Yeah. But we need to know what this V1, V2 is, right? Only then it helps, only then we can proceed and do it. But we know how to do that. So V1 will be equal to N1, number of loops on the first one, B times V1 times L. If you want, that can be an L1 too, but I think it's the same L. That's your quotation. And that's equal to N is 1. Magnetic field, I suppose, is 1.2 again.
0.01.
It's 0.01.
Oh, 0. And V1,
4 meters per second.
where are you guys reading? Oh, here, 4 meters per second. And L,
L is
12
12
centimeters.
centimeters, that's 0.12. Okay. That, so this is 1.2 into 4, that's 5 milliamps, 5 millivolts. So correct? Did I do that one?
I believe so.
Please.
0.05.
0.05.
Oh, 0.05 or 0.00?
I got 0.5.
Oh, then it's wrong, so it's 50.
We'll try this again. 48.
I think it's.
I got.
Nah, it's still 0, my bad.
Zero, zero.
Yeah, okay. So it's 5 millivolts, right? Okay. So like V2 now, similarly, is N2 times V times V2 times L. Pretty much the same, and N is the same, magnitude is the same. V1 is probably different.
Yeah, let's do
2.
Yeah.
This is. So it should be half of that because 4 rotation is it's 2.5 millivolt. Okay. So now we know voltages V1 and V2. Now it's a old Kirchhoff's law. But we do the loop. So we say this is current I1. That's current I2. And here this will be I1 plus I2, right? Using Kirchhoff's law at the junction, it has to be added up. So we can say loop 1, we will get V1 minus I1 R1 minus I1 plus I2 R3 is equal to 0. We are looking for the current set, suppose it's determine the direction of magnet, the current and resistance are 3. So we are only find 3, I suppose. But all these resistances are the same. Colors. That's R. And yeah.
So then we're just plugging in.
No, we have 2 equations now, right? So let me process this a little bit. So I have 2 i's, and so let me take it to the right hand side. So it is 2 times R. So I1. It is 2 times R times I1. That is an I2. So it is minus R times I2 is equal to V1, so plus. Or actually plug it in, like that's what we misunderstanding. I think let's plug in the numbers. So it is 5 millivolt, remember? So it is 0.005 minus R is 5, I suppose.
Yeah.
So it is I1 is 5 minus I1 times 5 and minus I2 times 5. That's equal to 0. 5 cancels out, and this makes it 0.001. And that is 0.0010 minus I1 minus I1 minus I2 is equal to 0. Take it to the right hand side, or keep this and then change it again. So it's 2 times I1 plus I2 is equal to 0.010. So that's just one equation. We cannot solve it still. But there are 2 unknowns in it. So that's for loop 1. Do the same thing for loop 2. Any questions over here? Right, I wrote this down saying V1 minus so much minus so much.
Okay.
And current I1 I1 plus I2 times R3.
Mhm.
And we are interested in I1 plus I2. But for that I need I2. Do the same thing for V2, go the other way. So it is V2 minus I2 R2 minus I1 plus I2. R3 is equal to 0. I2 is not a 2.5, right? That is 0.0025 minus I2 times 5.0 minus I1 times 5.0 and minus I2 times 5.6 is equal to 0. So 5 will make it 0.00005. 3 zeros. 5 minus I1 minus 2 times I2 is equal to 0. That is I1 plus 2 times I2. Okay. So we have to solve these two equations. I think good would be to they multiply this by 2 and then subtract it, right? So multiply this by 2 and then subtract. So that makes it 4I1 minus I1 is equal to 0.002. 0 minus 0.075. So that's 3 times I1 is equal to 0.0015. I1 then is equal to 3, 0.0003. That's 0.3 milliamps. If I1 is so much, and put that in this 0.0003 plus 2 times I2 is equal to 0.0005. So 2 times I2. I2 is equal to 0.2 milliamps. The question is asking for I3. I1 plus I2. That's 0.5. That's all that is being asked. Okay. That was the main purpose for the recording. And you guys, as promised, you were very quiet.
That one's daisy.
That was too long, right? I chose the right problem to not give the solution. No, I think that was not the point. The reason why I did not give the solution is this was asked last time. And I think it is not perfect, like cash, not a big deal, but I think I did not give the resistances. And then it's slightly dubious in a sense.
Did you mean to say 2I2 equals 0.002 amps, because wouldn't that make it 0.001? Or did you just accidentally write 2I2?
No, 2I2 times this is like 3 goes to the other side, 5 minus 3, that's 2.
Yeah.
And so what's the question? This is the question.
So 2I2 equals 0.002. So then the answer should be I2 equals 0.0.
Okay, yeah.
No,
So you divided by 2 to get I2.
Oh, 0.1, yeah. Yeah. Very good, yeah. Thank you. So 3 plus 1, so that's 4. Yeah, thank you, thank you.
Look at you, that's your credit right there.
Yeah, I'll add on to my test score. We are, and so,
That's Ashley's favorite problem. I think she did very well on the exam also, like you did.
me?
You.
Oh, yeah, these are my favorite problems. I like, this is the only thing I understand is making the loops. But yeah. So we're saying that's I3. True,
Oh my god,
and it's in the right direction, so, okay.
I think you should just like not test us on 5 and 6.
That's just a 5 and 6.
Yeah, I don't understand 5 and 6.
I think we should just, just call it off the exam. Call it off the exam. I'm working for the class, not just myself, I'm for the people.
Is there an easier way to explain it than what you did in class?
Which one? Number 5?
Oh, it won't be on the exam.
It's not?
That's what we're shooting for right now.
Oh.
No, that's how. Not.
Okay, is there a simpler way to explain 5 and 6 than what was done in class, because that was very hard to follow.
Must be, yeah, you can try it again. Which one? Yeah.
Everyone wants to know the basketball scores, 54 to 27.
There we go.
Are we losing?
No, we're winning.
Do we win?
Little Rock?
We're winning.
Nice.
What is this?
That's that wrong.
But you still have some, or they start back up.
Nice.
There we go.
Is someone playing in from our class?
Oh,
No.
that's funny.
No.
What do you play? You are an athlete. Huh?
Yeah, she athlete too.
Yeah, I know. Like some of you.
She's a power lifter.
No.
You are also an athlete?
No.
Okay.
I've been asked if I was an athlete just because I hang out with you guys so much. So, are you an athlete? You're
You should just start saying yeah. There's, you just say yeah.
Yes.
It would not know the difference.
Yeah.
So it's only 3 of you, no 4, right? Farida is also.
Mhm.
Oh, and
And
Brandon.
And Brandon. Yeah, that's correct.
Sorry, Brandon.
Oh, and Dyson.
Oh, yeah. Oh, and
What is he doing?
Any other back in the field.
there's no
There's another, I feel like there's more driving people.
Doesn't
Yeah,
something
there
like
was.
golf in our?
oh, that too.
Mhm.
And then there's Daniel Norris. Yeah. Oh, that dude's strong.
What
He's
is he
strong.
doing?
He's strong.
Oh,
We got a lot of athletes in them.
So, notice that the primary point or the equation in this whole chapter is what is called Faraday's law of induction, which states that induced voltage is the negative sign, but usually often we talk about magnitude of that. But negative sign means that it is opposing the system, and it is equal to number of loops times the rate at which the flux is changing. So think of any loop, if the flux is changing, flux means flux of the magnetic field is changing, that means it will act like a battery. Right, that's a main idea. Here, the point is, if you keep 2 loops in the same magnetic field. So let's say there is, let me try it somehow. So this is, there are n terms here, and let me next. This is supposed to be having the same radius. Okay.
Green.
Let's get that.
Yeah, my funny ball on here. I hit it like on like the corner.
Oh, yeah.
I feel it in my pinky. We're good.
Okay. I think sometimes when you're teaching, there is this chalk.
Older.
And sometimes when you're moving your hand, it hits you. It's very simple.
Yeah.
At that time, you can't do well because you're in front of.
You just like bunch about like posters on it, so hard, and you did that.
He probably hits it and turns towards the board.
Okay, even though I have not shown it properly, it's expected that it should be the same flux, so that the area should be the same. So both the areas are exactly the same. If that is the case, then rate of, if both the loops have the same area, that means it's the same flux. So if it is changing, it is the same change. So the change in flux in the first one is the same as the change in flux in the second one. Is that clear?
Yeah.
So they're two separate coils.
They're two separate coils, but since the area is the same,
The
the
ratio.
rate at which the flux is changing must be the same.
Two separate coils, basically.
Two separate coils with the same area. With the same flux, that is important.
There's this same flux, so area is the same. Okay, got that.
If that's the case, then using Faraday's law, V over N should be the same. So voltage induced in the first coil over the voltage induced in the voltage induced in the first coil over the number of loops in the first coil should be the same as.
No, you have it right the first one.
I said it wrong.
You have it on here as V1 over V2 equals N1 over N2.
Oh, that's the same. V1,
Oh.
V2, and 1. Yeah, but if you use this is the confusion you will make.
Okay.
Correct. And that's it. That's your equation.
Or to show that there's the ratio there.
Yeah, now the point is look for what is given
Mhm.
and you can, you'll be given 3 quantities and one will be asked for. Okay, this is how it transforms. Yeah.
Okay.
So look for the numbers that's given to you.
So determine the ratio of
So
the in the two coils inside the transformer.
So what is given is V2 is 10 and V1 is 120.
And we want to know the number of turns.
So part A is, so with N1 over N2 that is asked or N2 over N1? Determine the ratio of the turns in the two coils. It doesn't matter whichever way it is. So we will do N2 over N1. N2 over N1 will be equal to V2 over V1. V2 is 120, I suppose. And
V1 is
10.
Oh, wait,
The way around.
sorry, V2 is 10, V1 is 120. Sorry.
10 over 120. So that's 1 over 12. If you want to take and write it as a fraction, also doesn't matter.
okay.
How you write it. Okay. Now, second is the device pulls a current of 120 milliamps. Determine the current coming out of the valve. Since the energy is conserved, we also know that I1 V1, so whatever is the power on this should be the same as the power on the second one. That should also be true. That's because power in the first one, power is rate of change of energy is same. And the two. So that means that V2 over, so this will be I1 over I2 would be equal to V2 over V1. Rewriting that. Put that back in there, but we know that V2 over V1 is N2 over N1. So that's equal to, or we should write it in the same form, but we should find I2 over N1. So I2 over I1 would be equal to V1 over V2. V1 over V2.
V1 with 120.
So that is 12 over 1.
Yeah.
That's not that hard. It's easier than this problem.
My problem is I don't know which eye is coming out. Of
Ah.
the thing or which one.
Oh, yeah. So usually this is not the, so this is to motivate the fact that this is the same.
Mhm.
How usually the diagram looks is that there will be an input.
So the answer would be is 12.
So
right?
this is
Yeah.
input. And there is an output. And I chose that this is 1, that's 2. That's all there is to it. And if you're confused that what if this is up or down, just be consistent. I don't think the problem tells it very clearly that whether we have to find V2 over V1 or V1 over V2. So if you find V1 over V2, then you'll get 12. And here you will get 1 over 12. That's okay, as far as it's not specified clearly. If the question asks that find the voltage in the second loop with respect to the first loop, then you are doing this. Is that the confusion? Does it help?
Yeah. Then with the part B, where
Yeah.
it says like determine the current coming out of the wall socket.
If it pulls,
This is input means wall socket, right? Like this is how you will connect your, so that's your wall socket, that's what I meant.
Okay.
and that's your out.
This is output means this is going into your device, maybe. That's
So-
your phone.
So I2 is equal to 120 milliamps, which they give us, so then we solve the problem.
Oh, yeah, there is a more information. I thought it was
Yeah.
done. Oh, okay, so.
That's what we're saying, we didn't know to put 120 for the.
Oh,
I2
that's
for
what you've
I1.
been telling, and I'm not understanding what's, sorry, okay. Okay, if the device pulls a current of 120, yeah, if the device, oh, so your point is that is it I1 or I2? I1 is given as input. Oh, that's not clear, right? No, hold on. So the wall output is, wall socket is V1. Right? Plugged into a wall socket that is 120 volt. So V1 is 120.
Mhm.
Right. So we are interested in finding I1. Correct, or I1 is 1 now. If the device pulls a current, no, I1 is 120 milliamps. Yeah. All right.
Wait.
Test, will you just tell us?
Yeah, would you write it that confusing, because that's what, where the wording, like, it says. It what pulled, but then determine the current coming out.
Whenever there is a confusion like this, ask me in the class.
Okay,
Okay, if I like, for example, in this problem, the moment I read it, I will understand, oh yeah, this is not clear. And then I'll tell it to everyone. Right, or I will make a judgment there that no, this is clear, so I won't tell the answer, I won't tell it to you and I won't tell it to anyone. But by chance, if I figure out that there is really, then I tell it to everyone and tell it to you.
okay,
Is that,
Yeah.
Okay,
so this one, I1 is 120.
I1 is 120, so I2 would be equal to 12 times I1, which is 12 times 120.
It's milliamps, so
Yeah, 1440 milliamps, and that's 1.44 amps.
Last two.
last two, there's only one more.
Eight. Look at that.
Okay. Let's okay. Problem 6.
Nothing that's wrong, wrong.
Hmm?
I don't know what's happening.
This is the first problem where the angle, I think one of you guys was asking.
Well, how was zero?
Yeah,
No one
then
did.
is it not 0? So this is a problem where it is not 0, so we are a little careful. So that's. It's notated. Now, as you're rotating, what is changing is this area. That's your area that is changing. That's the current. What's the question? It's the direction being asked. So, induced voltage is equal to N times rate at which flux is changing. Flux is magnetic field times the area and the angle at which it is. So it is, if you notice, this one makes an angle, right? As it is rotating, it makes an angle. So that is equal to cosine of theta. Where theta now, you say, is omega t. So everything is constant except the theta. So the cosine theta, when you take a derivative, that becomes sine theta. Change the sign, and d by d theta, that it brings in an omega. Pause, is that what it said? Okay.
Are you just deriving the equations that they gave us?
I don't know, I mean, I'm not doing it, right, roughly get the, yeah, so that's the. Yeah, so that's the equation that they give us. Okay, like you guys determine the maximum induced voltage. Yeah. Okay. If I write it in that form, so this is.
So anytime there's like any circular object, it's gonna be sine or cosine.
If it is rotating.
Rotating,
If you
yeah.
see the rotation, then it is sine and cosine. Let me, since theta is omega t, let me rewrite this as n b a omega. I move it this side, and that is sine omega t. Correct. In the part A of the problem, it's asking for V max. This can change from +1 to -1 because it's a sine function. What is the maximum value of the sine function? 1. So it's the maximum value of this will be just setting this to 1. So this will be equal to n p a omega. N is 1, there is only one loop, but it could have many loops. B is given to be
10.10.
B is 0, yeah, 0.1. 0. Area, So this is area is half of this, right? So this pi r squared over 2. So it is pi times r is given to be 10 centimeters, so that's 0.10 square over 2, right? That's the area. And the 600 revolutions per minute, which is already given, and omega is given to be 20 pi. Oops. So that's 10 raised to minus 2, 10 raised to minus 3. So 10 pi square times 10 raised to minus 3. Pi square is 9 point something,
It's 9.8696.
9.9, right?
Yeah.
10 raised to minus 2. Volts. That's 0.099. Hopefully this works.
Yeah.
Okay. And it's also asking you to in part B plot this. We calculated only the maximum value. We did only the maximum value, but we can plot this as a function of time. So this as a function of time, if I were to plot this, then whatever is the V max that shows up here, that's your V max. Bottom will be minus V max. And this will be like this. I think that's your sine.
It's just because the sine wave. That
That's all, that's all. And the maximum value will be max. That's it. So that's your induced voltage. That's it. And when you're plotting, it is also important that you give this on here. So that's theta is equal to 1 period, right? So this will be 2 pi over omega.
Wait, 1 period. How do you know it's a pi over omega?
Because time period is 2 pi over omega.
Or that's something you have to know.
Yeah,
Okay.
like time period and frequency are related. That's long.
I think you should use. Oh my gosh, if you could have a class tomorrow. I was like, you should use class tomorrow as a review session.
Oh.
He's taking his day off. What you doing today off?